It was not so easy to work out how to pitch this talk because there are a few experts in exponential asymptotics on this program, and you already had a masterclass from Saleh, and Scott's given a number of talks, and John King is around and knows exponential asymptotics. But I thought I don't really want to talk to just the experts, so I pitched it at everybody else. So I apologize to Scott if it's a bit boring for him. And I thought, even though you've heard it a few times already, it can be a bit mysterious, this selection by Stokes lines and complex planes and things like that. So I thought you wouldn't mind hearing that sort of thing again. And in fact, I was going to try and anchor it on something which everybody might be familiar with. So I wanted to talk about some linear and nonlinear eigenvalue problems. And I want to start with a linear eigenvalue problem that I hope is familiar to everybody from their undergraduate days. And I sort of want to say that the selection of Chapman-Taylor fingers is really the same problem as this problem. It works in exactly the same way. So what's this problem? It's a quantum harmonic oscillator. So this is the equation that I want to solve on the whole real line with f going to 0 at infinity. And I'm interested in, it's an eigenvalue problem, I'm interested in what the eigenvalues lambda are. And I'm going to do asymptotics in the limit that the eigenvalues are large. So I'm interested in lambda tends to infinity. And so I'm going to normalize the problem. I'm going to rescale distance with lambda, and I much prefer to have small parameters than large parameters. So I'm going to call epsilon to be 1 over lambda, and that just recasts this problem in this form here. So epsilon is now the eigenvalue, and epsilon is going to be tending to 0. Put this in especially for John, and he's not here. The Liouville-Green approximation that everybody else knows as WKB.
He might be watching at home.
He might be watching at home. So if you do that approximation on this equation, it's the standard thing. You get the iconal equation for the phase function phi here, and then you get a hierarchy of amplitude equations, of which this is the first one. And so you can solve that. The iconal equation is just first order, so you can just integrate it, and you can always solve the first order amplitude equation in terms of the derivative of phi prime. You find the solution there. Of course, I've got plus or minus here. I've got two independent solutions to the equation, and so I now want to impose the conditions that it vanishes at infinity and minus infinity. So if x is less than 1, then I should choose that. Remember, it was e to the I times the square root of 1 minus x squared. So I have to decide whether to choose that to be plus or minus, and it turns out that I'm going to write it as x squared minus 1 if x is less than 1, so I'm taking the square root of a positive number, and then I want a plus sign in order that it decays as x goes to minus infinity. And likewise at this end, I want the same thing but with a minus sign so that this decays as x goes to plus infinity. And then in between minus 1 and 1, I can have both of the oscillatory exponentials. So I've got a plus and a minus. And so each of these have got arbitrary coefficients. So in principle, I started off with 6 arbitrary coefficients, so 2 coefficients in each region, and I've used the boundary conditions to get rid of 2 of those. So in order to finish the problem off, I've got to connect the A0 to the A1 and the B1 and the B2. And you do that by matching in this region near the turning point, so at x is minus 1 or x is plus 1, where the WKB approximation breaks down. So it's a sort of standard problem. The local behavior near those turning points is an Airy equation, so it's an Airy function. And so you want the solution which, for example, here it's got to be exponentially decaying as y tends to infinity, so y is my local variable. And that tells me, when I track back the asymptotics of the Airy function going the other way, it tells me what the multiples of the 2 oscillatory exponentials are in terms of the multiple of the decay. And so I think I'm calling phi here the exponent with the plus sign. Then this tells me that it must be A1 minus IB in order for to match with this, it gives me this condition on the A1s and the B1s. And if I do the matching at the other end, it gives me this condition on the A1s and the B1s. So that's a sort of, I haven't shown you all the details, but that's a sort of standard problem in matched asymptotic analysis, and you find then now for a non-zero solution, these are two pair of two homogeneous equations, so the determinant of that little 2 by 2 system must be 0 in order to get a non-trivial solution. And when you work out what that determinant is, you get this condition now for your, this is the eigenvalue condition. So phi 1 minus phi 0 divided by epsilon must be 2n pi plus 1 because of the minus 1. And so if I invert that, the eigenvalues are 1 over epsilon. And this difference between the phi's, of course, is just the integral of this function, which was phi prime. And you can do that integral. It turns out that your approximation for the eigenvalues lambda is lambda n is 2n plus 1. And that approximation is valid in the limit that n tends to infinity. In fact, it turns out to be exact in this case. Those are the exact eigenvalues and those are the exact eigenfunctions. And so indexing eigenvalues by n comes up all the time, and it's even related to the sort of harmonics on a guitar string. Effectively, you're saying that I've got a wave, each of those oscillatory exponentials corresponds to a wave. It comes in, it hits the turning point, and it bounces and goes backwards. And when you've done that twice, the condition is that you must have got back to where you started. The wave goes in, reflects again, you go back to where you started. And the reason it's 2n plus 1 and not 2n is because I have a phase change of pi over 2 as I reflect at a turning point. So I hope that's sort of familiar to everybody. It's a recap of undergraduate matched asymptotics. I want to look at what happens to the same problem now when I go off into the complex plane. This is a complex analysis program. And in order to do that, I want to remind you about Stokes' phenomenon, which arises as it's sort of the interplay between asymptotic expansion and analytic continuation. So you take an asymptotic expansion. When you analytically continue it, you need to know about Stokes' phenomenon in order to get the right answer. So let me just illustrate Stokes' phenomenon by way of integrals. So this is a standard example to illustrate Stokes' phenomenon, the complementary error function. And so here I'm plotting this integrand here. So the height here is e to the minus is minus t squared, and the color is actually the phase. So the height is the real part of minus t squared, and the color tells you the imaginary part of minus t squared. And so this is an integral from, there's the point z, and it goes off from z to infinity. And if I wanted to do an asymptotic expansion of this function, I would I'd do an end point, deform to the steepest descent contour, and then do an endpoint analysis. Most of the contribution comes from the point which is highest. This is minus t squared. I'm then taking the exponential of that. So all the contribution comes from the endpoint here, and the local analysis gives you a good approximation. But if I now swing z around in the complex plane, then you can see what happens to the steepest descent contour. So whenever I cross this col here, then the steepest descent contour falls into the wrong valley. It goes off to plus infinity instead of minus infinity. And so when z is on this side, I still get the endpoint contribution, but in order to get the end of the contour back to plus infinity, I have to include this contribution over the saddle point. And so I get an extra contribution. I get the endpoint contribution and the saddle point contribution. And the relative size of each contribution is determined by the relative height of the endpoint and the saddle. And so you can see as z crosses over, the endpoint has to be higher than the saddle. So the saddle is exponentially smaller than the endpoint contribution when it first appears. But then when this endpoint dips down below the horizon here, the saddle is the highest one. So if you didn't know that you had to include it, and you just included the endpoint contribution, you'd be completely wrong by the time that you've taken z all the way over here. So that's the standard example. I want to use a sort of even simpler example. The reason I guess this is not quite the simplest, the standard example, is that this function is analytic now. I want to use the exponential integral. So it satisfies just this first order differential equation. So if I use an integrating factor, I can again write it as an integral. And so the exponent is even simpler now. This is just the real part of t, and the phase is the imaginary part of t, but I sort of included the 1 over t in there as well. And so you see you've got a pole at the origin here, and the steepest descent contours are just parallel to the real axis. So this is now z real, and this is z imaginary in that direction. And what happens this time as I swing round is, of course, as I cross the positive real axis, I end up picking up a contribution from the pole. So you can think of that as, oh, there's a branch branch cut here with this white line, so you've got to get the contour back over and back round again. Or you can just think that I picked up a pole. So if I do an asymptotic expansion of this function, I just integrate by parts, if you like, or I do the endpoint contribution, you get this series solution in inverse powers of z. And so this needs to be there all the time, but if z is in the upper half plane, I need to add on the contribution from the pole. And the contribution from the pole just picks up 2 pi I times the e to the minus z, so the residue of e to the t over t, but t is 0 is just 1. And of course, you see, if you keep going round, you keep picking up an extra one every time because it's got a log singularity in z is 0. So the asymptotic expansion of the exponential integral sort of looks like this. So I start off with this inverse power series in 1 over z. As I cross here, nothing happens. As I cross the Stokes line, then I pick up this extra term, this e to the minus z, which sits at the end of this series. So I've got infinitely many terms here, and then I've got e to the minus z. So it's beyond all orders of this first series. And I don't notice it until I cross the imaginary axis when e to the minus z goes from being exponentially small to exponentially large. And so suddenly it's now at the front of the series. And if I didn't know that I'd turned it on here, I'd have a terrible approximation by the time I got here. So let me go back to the harmonic oscillator and try and look at what is that solution looking like in complex space. So this is the real line here. And so I've got various plots going on here. This is a plot of the two-phase functions. So I remember e to the plus or minus times that integral of 1 minus x squared to the half. So one of these is the plus and one is the minus. And as before, the height tells you what the real part is, and the color tells you what the imaginary part is. And the joining points here, those are the turning points. So this way you've got these three things joining on here is exactly this turning point here. In between, along the real axis here, these two are both order 1. We had 2 oscillatory exponentials there. So that's why this function is, the height is uniform there. And then as I come out here, I've got one exponentially large one and one exponentially small one. And it's likewise on this side. I'll spin this in a minute so you can see what it looks like. This picture here is showing you the Stokes and the anti-Stokes lines. So the Stokes lines corresponding to that local solution, the area solution, they come off at angles of 2 pi over 3 and 4 pi over 3. And so what you find is that if I start with the exponentially small solution here, as I go around here, it becomes exponentially large when I cross this dashed line. And then, as it crosses this Stokes line, it turns on a multiple of the exponentially small solution, which is just the exponent with a different sign. And by the time they get to this dashed line here, they're both order 1. So that shows you as you go around here, you started with 1 exponential, but by the time you get to the dashed line, you've got 2 again. And if you carry on going round, they switch dominance on this anti-Stokes line here. And the one you turned off is now the big one, and by the time you get to this Stokes line, you lose the contribution from the one you started with. And the little twirly line here is supposed to indicate that's a sort of the square root nature, if you like. It's a 3/2 power. So as you go all the way around, you started with the small exponential, you end up with the big exponential. So you know that as you go all the way around it, you can't, you must stop with the solution before you get back. So the line sort of indicates which of those solutions are present at any point. And that's what this picture down here is showing you. It's this picture, but I've cut, and I said I don't want the one which is exponentially large here, and I don't include it until I get to this Stokes line. And likewise, I come around here, I don't include it until I get to this Stokes line. So you have these regions of space here, you only have one of those exponentials, and in the middle here, you've got both. And that's what this picture is showing you. Let me just spin those so you can sort of see what they look like. So you sort of see you get the saddle, and then you get the two sort of leaves that come down one either side, and that's this region up at the top and this region down the bottom. And so you can understand that eigenvalue condition. If I chose a path that went from minus infinity here, suppose I just, in the complex plane, I can avoid these turning points completely. So if I drop down and I come across here and I come back up again, I can do such a path and there's nothing to stop me. And what happens is that as you come across here, you turn on something which is exponentially small, which is the other exponential, so the other WKB approximation. And then you've got to exactly turn it off again when you get to this line. Because if you didn't turn it off again, it would be exponentially large by the time you go back to the real axis. So the eigenvalue condition is whatever you turn on this Stokes line, you've got to turn off on that Stokes line. And you can do the whole thing in the complex plane. So the multiple of the bad exponential that I turn on across the first is just I times whatever this thing evaluated at -1 is. And the multiple across the second is the same thing, but I'm now centering on 1 instead of -1. And so if I add those two multiples together, I must get 0, because otherwise my solution would be exponentially large at plus infinity. And you can recognize that this is exactly the same condition I had before. So all I've done is reinterpret that condition by not just doing it on the real line where I had to use maths asymptotics to go between the two turning points, but I've avoided the turning points completely, provided I know about Stokes lines and Stokes phenomena. Okay, so I want to now see if I can use that idea on problems where the turning points don't behave very nicely, but the Stokes lines are still accessible. But to do that, I need to know how to find Stokes lines and how to work out what gets turned on. So what multiple is it that gets turned on across a Stokes line? And so I need a technique which is available when I don't have integrals that I can see what's happening to the topology of the contour. Suppose I just have a differential equation. How do I identify where the Stokes lines are? And so one technique for doing that is this technique of Stokes line smoothing. So I want to convince you that the asymptotic expansion that you have contains all the information you need already. So if I took the endpoint contribution to the exponential integral, I said, oh, you just integrate by parts and you can work out its expansion. I wrote down the first 2 or 3 terms. So this is what the full expansion of the exponential integral is. And it's very nice and simple, which is why I chose this example. So you can see that this series has got 0 radius of convergence. It's factorial of the power. So for any value of z, the series will diverge. And that divergence is a sign that there's an exponential lurking behind it. Some people worry about divergent series, but the truncated divergent series is very useful. There's a very nice quote by George Carrier that says, divergent series converge faster than convergent series because they don't have to converge. And what he means is that with a divergent series, an asymptotic series like this, the first term gets you close, the second term gets you a bit closer still, the third term gets you closer still. And so the size of the terms is getting smaller and smaller. But eventually, you pay the price for that, and the factorial wins in the end, and the series diverges. So I need to truncate the series if I want it to be a good approximation. And so let me just write f to be a truncated series plus a remainder. So if I just fix n here and truncate, then how big is the remainder? Well, it's as big as the last term that I didn't include, so it's z to the minus n. But I could also let this truncation point depend on z. And therefore, if z gets a bit bigger, I take more points. If z is a bit smaller, I take fewer points. And so if I do that, if I truncate optimally, you find that the remainder term here is exponentially small. So where is the optimal truncation point? Well, you see it in the picture here. Terms are getting smaller and smaller, and then they start to get bigger. So I want to truncate about this term here, right? Where the terms that I'm adding, I've just got to the least term, and they're about to start getting bad. So at the least term here, the ratio between two successive terms is 1. And so if I look at the ratio between successive terms in the series, it's, well, I multiply by n, I divide by z. So that tells me that the optimal truncation point here is where n divided by z is 1, order 1. So the least term, I need to take z terms, mod z terms in this term. So what I want to do, I want to show you one calculation, which is to truncate optimally and look to see what happens to the remainder. So I can write down the exact equation for the remainder, and I have now an inhomogeneous equation. So this is due to the fact that the truncated series doesn't exactly satisfy the differential equation. And now z is complex, so I'm going to write it in polar form as r e to the I theta, and that's because the optimal truncation point depends on the modulus of z. So n can now just be written as r plus alpha. Alpha is just there to make it an integer, where r is not necessarily an integer. So alpha is bounded as r tends to infinity. And then I'm going to use Stirling's formula on the factorial, and when you do that, you work out what this thing is, and it turns out to be this. So you see that e to the minus r in there, it is exponentially small, as I claimed. Well, unless here it is exponentially small. So the homogeneous version of this equation has got solutions which are e to the minus z. And I'm expecting one of these to be turned on. So I'm going to write this remainder as some function s, the Stokes multiplier, multiplied by this e to the minus z. And then I've got a choice of how to write d by dz. So I've written z in polar form. So I could write that as d by dr or d by d theta. I could do x and y. Because the n is a function of r but not theta, I'm going to write it in terms of d by d theta. And that means that if I keep r fixed and move theta around, n is not changing, it's just fixed. So I'm going to write d by dz in terms of d by d theta. So when you put all that in, the equation for the Stokes multiplier ends up being just this. So now it's still exponentially small, actually, apart from when theta is equal to 0, because I've got an e to the r, e to the I theta there. So it's minus r and then plus r cos theta. So that's negative unless theta is 0. And so I've got something which is exponentially small apart from when theta is 0, and then it suddenly becomes algebraically large. So if the derivative goes from being really small to being large to being small, that's a boundary layer. So I need to do a local expansion there, theta is equal to 0. And then if you Taylor expand this r e to the I theta here, so the e to the r here cancels with that one, and the I theta r cancels with that one, so the bit that you get left is the minus theta squared r. So locally, for small theta, this is what the equation is, and I know that there was no multiple of this contribution as theta goes to minus infinity, so if I'm before I've got to the real axis, so in the negative half plane, lower half plane, I guess. And so that tells me that when I integrate here, I integrate from minus infinity. So we see that S has got the form of an error function. It's an error function smoothing at the Stokes discontinuity. This goes back to Mike Berry in 89. And you can see that S goes from 0 to 2 pi I as r to the half theta goes from minus infinity to plus infinity. So as I cross the real axis, remember Z is r e to the I theta, so theta is 0 is the positive real axis. I explicitly see the switching on of this subdominant exponential term without any integral representation. So I guess this is how Stokes saw it, that you go from having 0 this is the real axis, this is the branch cut, this is the lower half plane, this is the upper half plane. So you go from having 0 to 1 as you cross the positive real axis. And that would be a discontinuous jump, and this is how Berry sees it, that the jump is not discontinuous, it's smooth, and it's parabolic profile, because because it's r to the half theta is the keep error. So you have this error function smoothing of this discontinuity. So optimal truncation gives you a way to identify exponentially small corrections even when you don't have an integral expression. So if I knew what the late terms of the series were, I could just do the same analysis and see where the Stokes line is and what gets turned on. And so whenever I've got factorial over power type divergence, I'm going to get this sort of thing happening. So it's interesting to see, well, why did I get factorial over power divergence? And so to show you that, let me just let me switch. So far I've sort of been doing a coordinate expansion. I've been doing the solution that z goes to infinity. For most problems, you want to do a parametric expansion, so you want a small parameter rather than a coordinate. So I'm just going to switch from one to the other by rescaling my independent variable with epsilon. And so now z can be fixed, and I'm just doing epsilon tends to 0. So if I'm looking at this equation, I see that it's a singular perturbation problem now, that the epsilon multiplies the highest derivative. And so that means if I expand in powers of epsilon, so I read off what the first coefficient is, and then to get the next coefficient, I have to differentiate the previous one. And that's going to be true whenever you have a singular perturbation problem, because the highest derivative is always going to appear as an inhomogeneous term in these equations. So the factorial over power is really Dalgout's theorem. It comes from continually differentiating a singularity. So I had a 1 over z in the leading order problem. If I continually differentiate it, I'm going to end up with n factorial over z to the n. I get a power of z every time I differentiate, and then because the powers are increasing, I get a factorial on the top. So the factorial over power divergence is typical of singular perturbation problems. It occurs whenever your leading order solution has a singularity. And so here the singularity was at the origin, but of course the singularity can be off in complex space. It doesn't matter. You're always going to get factorial over power divergence. So that leads you to a sort of general procedure. So you try a formal power series expansion. You look to see where the singularities of your leading order solution are. You only have to worry about the singularities of the leading order solution because all higher order equations are necessarily linear, so you can never introduce any more singularities. So I know that if there are singularities of phi 0, I'm going to get factorial over power divergence. So I then look to say, right, I'm interested in the late terms as n tends to infinity. Remember the truncation point n got bigger and bigger as z got bigger. So in this case, with an epsilon expansion, the truncation point would tend to infinity as epsilon tends to 0. So I'm only interested in what these things look like for large values of n. And so I'm going to make the ansatz that it's factorial over power. And it's almost the same ansatz, so it's very similar ansatz as the WKB ansatz that I started off with. Because when I make this ansatz for large n, I'm going to get an iconal equation for chi here, it's known as the singulant, and I'm going to get an amplitude equation for the A, which is almost the same as the equation. There are going to be a few unknown constants, and you'd get those constants by matching locally near the singularity. Often you can get almost all the way without knowing those constants exactly. And so sometimes they're important and sometimes they're not. But if you really want them, then you do have to do the local analysis near the singularity. And then once you've got that, you say, right, there's a Stokes line whenever chi is real and positive. Sorry, that used to be a chi. And I could go through the analysis again, but you can basically just read off what has to be turned on. So if this is the form of the late terms, this is what gets turned on. So let me just show you now a couple of examples of using this. I want to show you one linear problem, and then I want to show you one very familiar nonlinear problem and try to convince you they're not so different. So this is a generalization of the quantum harmonic oscillator problem. So I think people are still interested in this sort of thing. I heard Carl Bender talk about this back in the last millennium. And he was interested in non-Hermitian quantum mechanics, so models for which the operator is non-Hermitian, but you still get real eigenvalues. And what's the limit? In what situation can you do that? And if your operator is PT symmetric, so it's symmetric in momentum and time, then you you still get real eigenvalues. And this was his canonical example, where you, if p is 2, it's just the quantum harmonic oscillator gain, but p could be any integer or non-integer value here. So if you do the same trick and you look at the large eigenvalue asymptotic, so there's the usual rescaling, and I'm going to define my small parameter to be 1 over my large parameter, and you get to this version of the problem. It's very similar to what we had before. I haven't told you exactly where I'm applying the boundary conditions, but I will on the next slide. I'll be precise about that. So you can do the same trick with the WKB approximation. You get the iconal equation for the phase, you get an amplitude equation for the leading order amplitude. Again, you can integrate this, and again the amplitude is just 1 over 5 prime to the half. And this phase is in general, on the real axis, this would be complex now. Whereas when p is 2, it was real. So let me show you what path you want to solve this equation on. So you have to look to see where that phase function, where is it exponentially decaying and where is it exponentially growing. And you find that there are certain wedges. So this, in the p equals 2 case, provided I was in this wedge or that wedge, I had one exponentially decaying solution and one exponentially growing solution. And you just sort of, because you're now at fractional powers, you just watch to see what happens to those wedges as you change p. And you find that as you gradually increase p, so you get more and more of these, but you're interested always in the connection between going to the nearest valley to the negative imaginary axis on this side, and the nearest valley to the negative imaginary axis on this side. So I'm already forced into the complex plane here. So you might think already you've got to use some sort of different techniques to solve this problem. Let me show you what the eigenvalues look like. So this is lambda going up this direction as a function of p. So p is 2, the quantum harmonic oscillator is here. And you can see that they're all, I've shown you the real eigenvalues. So obviously, once these two nip off here, then you start to get complex eigenvalues coming out there. For p greater than 2, all the eigenvalues are real, and you get countably infinitely many of them. For p less than 2, you find that these branches gradually nip off here, and so for each value of p less than 2, you get a finite number of real eigenvalues, and then infinitely many complex ones. So, sort of because you get real eigenvalues, you can almost do this problem in the way that you did it before. So if you look at the place where phi is real, I said on the real axis is not real anymore, but if you take it from one turning point, and there's a path to the turning point in this quadrant to that one in this quadrant of this sector, on which phi stays real. And so you can sort of do exactly the same WKB theory. You sort of you go between this turning point and that turning point. You say I've got two oscillatory exponentials along that curve. I match with an area function either side. That tells me what the multiples are. And exactly the same argument works. And in fact, you get sort of the same answer. That the jump in the phase between one side and the other times 2 over epsilon must be 2n plus 1. That gives you a formula for the eigenvalues. This integral is obviously not quite as nice as it was before, but you can still work it out. In fact, you can still work it out analytically. So that's the analytic expression for the eigenvalues. This is what Bender had done. And this is what this is when you plot it. So you can see it does fairly well, but it doesn't have the pinching off of the branches. And if I plot the eigenvalues on there, it does really well for values. Certainly for values above 2, it gets them all perfectly well. And even for below 2, it's doing all right until they pinch off, and it just doesn't quite capture the fact that they're about to disappear. And so why is it going wrong when p is less than 2? So for p is less than 2, this path that I said you can track between a and b goes through the branch cut. So if p is less than 2, I have a fractional power of x at the origin, so I've got to put a branch cut up, and because I'm working from down here, I'm going to put the branch cut up the imaginary axis. So you cannot get from A to B on a path where phi is real that does not go through the branch cut. So that's the reason it fails when B is less than 2. What about if I think about the Stokes lines? So near each of these turning points, it's the usual airy type behavior. I have 3 Stokes lines coming out of there. And there's nothing to stop me now, starting down here, tracking up through these Stokes lines and then going off to the valley down here, and just keeping track of what gets turned on or off across the Stokes lines. And the key observation is that I said that wherever the leading order solution has singularities, that generates a divergent series, and a divergent series generates a Stokes line. So this time, I have the usual 3 half singularities at the turning points. I also have this singularity at the origin because of the branch point there, and that generates a Stokes line, and that's what's missing in the classical analysis. So let me just run through that calculation. So this is the WKB approximation. We've already seen what the leading order amplitude is. This is what the equation for the general nth term in the amplitude is. I know it's going to diverge as factorial over power, so let me make that ansatz. So here's the factorial over power ansatz. When I substitute that in and equate coefficients of n, now remember this is as n tends to infinity, then at leading order you get an iconal equation for this chi, which is not too different to the iconal equation I had before for phi. And in fact, the solution for chi is just that chi is a multiple of phi prime. And I know that A is singular at one of the singularities of the leading order problem. So that tells me the boundary condition on this equation, that I know that chi must be 0, so A must be singular, at one of the singularities of the leading order problem. So either one of the turning points or the origin. And so it's not so surprising actually that you get this to be twice 2I phi. And that's because it must be well, you see when we turn something on, I've got to turn something on which is a solution of the equation. So it's got to be one of the WKB solutions. So whenever you get this singulant, it has to be the difference between 2 of the solutions you had to your old iconal equation. And that's why, because they were plus phi and minus phi, I have to get twice phi in here. And then you carry on and you do the amplitude equation. And in fact, you know what the solution to the amplitude equation is as well in this case, because you know it has to be something that would satisfy the original equation if I stuck it in. And so it has to be the same form as I had before, and indeed it works. So that tells you immediately what the late terms are, subject to this constant. And also the offset here, I don't know what the gamma is here. And so, based on that Stokes smoothing analysis, I know that there are Stokes lines wherever chi is real and positive, so that means where I times phi minus phi naught is real and positive, and I can just read off immediately what gets switched on. It's just e to the minus 2I phi minus phi naught times this stuff. And now you see exactly what I was saying, that this is an e to the I phi over epsilon, but I'm turning on e to the minus 2I phi, there should be an over epsilon there, and therefore I get e to the minus I phi over epsilon. So I can see immediately what's turned on, providing I just work out what these last constants are. And to do that, so to work out what the gamma is, you just got to make sure the singularity has the right order, that it's consistent with what you would get when n is 0. So it's increasing by 3 over 2 every time. You've got to make sure it's consistent with what you started off with. And so you just look at what the solution for A naught is, what you've got for AN, and you say, well, if n was 0, this would be 3 gamma over 2. And it's 0 there, so I must have gamma is 0. I'll make sure that they're consistent. And then to work out what the lambda is, the big coefficient out the front, you have to do the local analysis. And when you do that, so that's sort of the airy function matching, if you like, again, that gives me 1 over 2 pi. The local solution is still an airy function. So that's all classical. The slightly different one is the origin. So now what happens near the origin? So you work out what chi is doing near the origin, and it doesn't have any singularity, it just looks like x, but the amplitude has a singularity. And so you say, this is what A naught is, this is what I had for AN, so for these to be compatible, gamma must be minus P. So when I put N at 0, I get x to the P in there. And then to determine what the coefficient lambda is, you've got to match with an inner region. So let me just show you how that works. It's not so difficult a calculation. So based on the fact that I'm going to rescale x with epsilon, and there's an x to the p here, I'm going to say A is equal to 1 plus epsilon to the pg. You stick that in and G satisfies this equation. And then this condition here tells me that G should be minus y to the p over 4 as y goes to infinity. And so now I've got that equation for G. I could solve it, but really all I want to know is what does it do when I match outwards? So I expand that equation in inverse powers of y. And that gives me a recurrence relation for the coefficients. Because I'm dealing with linear equations, this is a nice, easy recurrence relation. I can just iterate it and solve it. So I know that this is what the outer limit of the inner solution is. This is what the outer solution is when I write it in terms of the inner variable. And then I look to see what do I have to do to make those the same. And you just have to choose this lambda to be this value. That tells you what the multiple of the bad exponential turn on across that middle Stokes line is. Okay, so when you go back to, you now cross the first Stokes line, the middle one, and the last one. This is the final multiple that you have of the bad exponential, the one which is going to grow at infinity. And so the condition is that this thing should be 0. That's the eigenvalue condition. So if p is greater than 2, then these two turning point contributions exponentially dominate this contribution from the origin, because the turning points were lower down. They were in the lower half plane. They're nearer to the action. And that sort of explains why the classical analysis got the right answer, because the contribution of the extra bit that I've added is exponentially small, so it's not really doing very much. But if p is less than 2, then this thing exponentially dominates. And so that tells me that in the limit that epsilon tends to 0, there are no solutions. So that tells me that there are only finitely many eigenvalues. So I cannot do n goes to infinity for the real eigenvalues because there are only finitely many. So you'd think, well, that there's not much of an answer. All you've shown is that I've shown that they do nip off in the limit as n tends to infinity. But as usual, for asymptotic expansions like this, that if you just say, well, all right, instead of either taking just these two and saying this is exponentially small, or just this and these are exponentially small, let me just plot the solution of this thing is equal to 0 and see what I get. So if you include all of them, then this is what the prediction for the eigenvalues are. And if I plot that over the top of the numerically determined eigenvalues, you find that you get absolutely perfect fit. The only one that drops at all is if you track this one down, when you get near p is 1, it starts to get very large and it starts to deviate a little bit there. So that's applying the new technique to a now old linear eigenvalue problem. But I want to try to convince you that nonlinear eigenvalue problems are not so different. And so I'm going to illustrate that with the Kruskal-Seeger model, which you've seen so many times in this workshop already that I'm sure everybody is familiar with it. But let me remind you and try and illustrate why it's the same sort of structure that we've just seen. So this is the toy model for crystal growth, where you have a steadily translating needle finger, and you say the velocity of the surface is the curvature plus epsilon squared times the second derivative of the curvature. I'm never quite sure why they picked this, but I presume this is some sort of surface diffusion. Anyway, if you go and write the equation for the shape of the finger in terms of the angle between the normal and the x-axis, then you get this nice simple equation here. The curvature is just phi prime, and the Vn just gives you the cos phi. And for a needle solution, you want something in which, as you go around this way, the phi should tend to minus pi over 2, and as you go around this way, phi should tend to pi over 2. So if s is arc length here, as s goes to minus infinity, you get this boundary condition. Plus infinity, you get this one. So the first question is there a solution? And so epsilon is a small parameter, so you do your asymptotic expansion. Well, first you try epsilon is 0, then it's just a first order differential equation, so then you can write down explicitly the solution. The easiest existence proof. And this is what it looks like. So this is phi as a function of arc length, and then if you translate it into what it would look like in xy space, is what the shape of the needle would be. So if you use that as your starting point, and you try an asymptotic expansion in powers of 2 epsilon, you find that you satisfy the boundary conditions at every order. And so it seems like you've generated a solution to the problem, and then you realize that Amick and McLeod have proved that there is no solution to this problem, so you want to know what's gone wrong with my asymptotic analysis. Of course, a few existential problems when first appear in this problem. So what's going on? So here is my my needle solution. This is phi as a function of s. So I need to analytically continue first of all. And so you find that you have singularities. They're on the imaginary axis here, and they're logarithmic singularities, which is why you see this this tall Riemann surface. So I have logarithmic singularities here and here, so that is going to generate a divergent asymptotic expansion in exactly the same way that my turning points or my branch could generate a divergent asymptotic expansion. And what you find is that that divergent asymptotic expansion generates Stokes lines that are now centered at these singularities. And the Stokes line is parallel to the imaginary axis. So this singularity generates a Stokes line which comes down, and this one generates a Stokes line which comes up. And so when they cross the real axis, they turn on an exponentially small subdominant solution, happens to be oscillating. So it's exponentially small at the point where it's turned on, but it's growing at infinity. So it's one of these things not allowed at infinity, exactly like in my original problem. And so here I've got my Stokes line. Here the multiple of the small exponential is 0. Here the multiple of the small exponential is this thing. It gets turned on as I cross this Stokes line, and it's not allowed at infinity, because even though it starts like e to the minus pi over 2 epsilon, it's got a cosh s in there, so it's exponentially growing if you go far enough away. So unlike the eigenvalue problem, I've got no way of turning this off. I've got nothing to play with, so I just find that there's no solution. But there are problems that look very similar. So one way to fix that up is to look at the anisotropic version. So you say that surface tension depends on the angle, and so you end up changing this cos phi. This is now fourfold symmetry in there. And again, the leading order solution, you can write it down. Now you have to do it implicitly. It's this mess here. It doesn't look so very different. The finger shape looks very similar. It's just a bit more squat at the end. This is phi as a function of s. It's got a few more kinks in it, maybe. Now you find that there are 4 singularities, not just 2, nearest the real axis. So you have 1 in each quadrant, symmetrically located. And the Stokes lines are still parallel to the imaginary axis. So you still get a Stokes line between these 2 and a Stokes line between these 2. So now what happens is that as I track along the real axis, something gets turned on here. It's this multiple. It's oscillating. It's exponentially small when it starts off. It's got some amplitude function. R and phi here are just constants. In fact, r e to the I phi is the constant I was calling lambda before. It's just the modulus phase version of that. So this gets turned on across this Stokes line, and then at this Stokes line, this second multiple of it gets turned on. And so by the time you get to infinity, you've got to make sure that the combined sum of those 2 things is 0. Or another way to think about it is whatever got turned on across the first one had to get turned off across the second one. And so the condition for these 2 exactly cancelling is just the sign of this thing is equal to 0. So that's exactly the same as in the harmonic oscillator. Where you cross one Stokes line, you cross the other, and you say that the sign of the phase difference between them has got to be 0. That's exactly what's happening here. And so you get a discrete set of values of epsilon in this case for which there are solutions. So the only difference between these nonlinear problems and the linear problems is that the singularities have gone off into complex space. Whereas for the harmonic oscillator, the turning points were on the real axis. And if I wanted to do the Stokes analysis, I went off into complex space to do it. Here you're sort of forced to do that from the start. If you want to stay on the real axis, well, the singularity generating the Stokes line is off in complex space. But apart from that, they behave really very similarly. Right. I've got a couple more slides just on some of the, because this is all very old stuff by way of just introduction. Really, I've got some slides on what's vexing me at the moment, or what are the challenges with. So this is a simple technique. It's not the only way of doing these things. It works very well for some problems, and it struggles for others. And the sort of problems where all hell can break loose is when you move on from ordinary differential equations to partial differential equations. In particular, because the number of things that you can turn on suddenly becomes infinite. So when I've just got a second order differential equation, there are only two WKB solutions. So if I've got one, the only thing it can turn on is the other one. It's very simple. I just have to work out how much is turned on. If I've got a PDE, then I can turn on anything. And that can lead to some interesting extra things happening. So in particular, so I'm used to saying I've got an expansion. There may be more than one singularity of the leading order problem, so I may have one of these factorial over powers for each singularity. That's all right. Cope with that. You can get things like what I've called second generation Stokes switching. So in some ways, this sort of happened with the harmonic oscillator, that the first exponential turned on the second one, and then that one carried on, it became dominant, and it turned off the first one. So that sort of thing can happen all the time. You turn something on, and then it goes and turns something else on, and then that can turn something else on, and you've got to keep track of all those things. That's not too bad, but it does mean that sometimes, some of these are exponentially subdominant to the others. If the chi from one is different to the chi from another, then it's sort of exponentially further down. I've already gone to sort of exponential, and now I'm doing another exponential down. It can get very tricky. But the thing that really causes you trouble is something called higher order Stokes switching. And that's the idea that a Stokes line itself can be switched on and off. So sometimes a Stokes line can be there, and sometimes it can suddenly disappear. Now, if you grow up on second order differential equations, you're used to Stokes lines finishing either at the origin or a turning point or at infinity. And all those things you can see in advance, because the turning point is a nice big singularity of the equation. Right? So you see that there's got to be Stokes lines finishing there. This higher order Stokes switching means a Stokes line can just disappear. It runs into another Stokes line and then it just disappears. And it's associated with these approximations for the late terms. So if you have multiple things that can appear in the late terms, so this factorial over power ansatz is very similar to the WKB ansatz I started with, right? And so I know when I do WKB, sometimes the contribution I'm finding is there and sometimes it's not. It can get turned on and off by Stokes lines. So what happens with this factorial over power late terms ansatz is that sometimes the term you found is there and sometimes it's not, because a different one turned it off by a Stokes phenomenon in the asymptotic approximation of the late terms. So it's a sort of higher level, higher order Stokes phenomenon. And I just wanted to illustrate that using, so we played a few years ago with a toy. I wanted to do the time-dependent version of the Kruskal-Seeger problem. But then the real time-dependent version, if you really think of v as a velocity, is a nightmare. It's a horrible equation. So I thought, well, let me do something which has got the same steady state by just putting a phi t in the equation. Even that turned out to be a bit hard. So I removed the cos and replaced it by an inhomogeneous term, so that I had a linear equation that's got roughly the same steady state, and it's roughly the same Stokes lines in the steady state. So it had all the ingredients, but I could actually solve it by Fourier transform. So when you do the Fourier transform solution of this problem, you find you get three contributions. You get an n-point contribution, which is basically the regular asymptotic expansion that we're normally starting off with. You get a saddle point contribution and you get a pole contribution. And this is how they appear. So this is S and this is T. Real S, real T. So you find that there are Stokes lines where the endpoint can turn on the saddle and the endpoint can turn on the pole, and then there's a Stokes line where the saddle can turn on the pole. So if I come across here, for example, the endpoint's always there because the base asymptotic expansion. So the endpoint turns on the saddle, so I cross this red line and now I've got an endpoint and a saddle. Started off with just an endpoint. I cross the blue line and I've got an endpoint, a saddle, and a pole. If I go this way, I cross the green line and the endpoint turned on the pole. And then I cross the red line and the endpoint turns on the saddle. So I've got an endpoint, saddle, and pole, everything's fine. It's not so unusual that the saddle should not turn, so why does this blue line not extend here? Well, because the saddle's not here, so it can't be turning on a pole. The blue line is where the saddle turns on the pole, so that's not so surprising. The strange thing is this green line stopping here and not extending. The endpoint is there here. Why is it not turning on the pole as I cross here? It turns on the pole down here, but it doesn't turn on the pole up there. But you can see that it shouldn't, because at the moment everything fits together nicely. Whereas, because if the endpoint turned on the pole across here, well, the saddle can't turn it on then. I'd get too many copies of it. So it has to stop in order to fit together, but why it should not be there is quite difficult to see. And the nice way to see it, or one way to see what's going on, is through, I included some Borel plane plots. I thought Saleh would be here and he'd appreciate it. I've got 2 minutes. I'll spend 2 minutes just seeing if I can explain what's going on here, but don't worry too much about that. So in the Borel plane, it's a way of keeping track of which contributions are there or not. So you always, when you do a Borel transform on this problem, what you find is that you get an integral from the origin to infinity along the real axis. And the endpoint contribution is always sat there. It is the endpoint of that Borel integral. And then the other singularities, so this is Zs and Zp, they correspond to different points in this plane. And if ever they cross this real axis, that corresponds to where the Stokes line is, and suddenly I pick up that contribution. So you just have to keep track of whether these guys cross the real axis or not. So what happens as I go across the bottom here is that this pole crosses the real axis, so I pick it up. And then when I cross the red line here, the saddle crosses the real axis, so I pick it up. And so I switch on the pole and then I switch on the saddle. Nice and easy. Now the saddle, you see I've drawn it here, it's a branch point in this Borel plane. So the contour that I end up, I sort of go around the saddle and back out to infinity again. And so what happens as I go this way? Why does the endpoint not get turned on when it crosses into the upper half plane? So what happens is the saddle goes first, and so the pole, remember this is a branch point, so there's a branch cut usually going out radially from the saddle here. So as the saddle goes up, the pole drops onto the lower branch. And so it's now hidden as far as the endpoint is concerned. The saddle crosses up into the upper half plane, and then the pole follows it on the other branch, so it never hits this contour, it's on the bottom branch. And then eventually, the pole goes through the contour from the saddle point, and then comes out again. And so that's why the saddle ends up turning the pole on, and not the endpoint. Because the saddle goes first, the pole drops onto a different Riemann sheet. It crosses the real axis without the endpoint ever knowing it was there, but then when it comes out onto the main sheet again, it has to cross the contour from the saddle. Trying to keep track of all that is what causes a headache when you try and generalize this sort of thing. Okay, I better stop that. Thank you.
Questions for John?
Can you give a little bigger picture? So you showed this previous PDE. What type of this analysis can it show for some PDE solutions?
So why was I interested in that PDE? So I know that's a PDE for which there is no steady state solution. exactly like the finger problem. If I write down the time-dependent version, then there is a solution. So what's the large time limit of the time-dependent problem? Why is it?
And what is the answer?
So the answer is that there is so it's actually this line and this line. What you find is that there's, you turn on the exponential which kills you at infinity. There's a Stokes line that suddenly appears here. So it's not there at the origin. It's not there at 0 time. This is time. And you turn on a little exponential here, but then you turn it off at this line here. So you have these wiggles that are there in the Kruskal-Seeger problem, but they're in this confined region. But as t goes to infinity, this goes off to infinity. So there's no steady state. This region just gets bigger and bigger and bigger.
So we can have a symptotic form of these wiggles.
Yeah. And you can say exactly where they're confined to. I was surprised, so I was hoping that I might see tip branching and things like that. And you have a wiggle, it might grow. But what you find for this, I mean, I didn't put the real dynamics here, but you find that it's on one side, it's not both sides. For the real problem, it wouldn't surprise me if you get something which is more like this, so that you get wiggles on both sides. And what would that correspond to? So in the finger, then you would have oscillations confined between 2 points on this, and they would gradually get bigger and bigger, so that these oscillations would grow like that. So you would sort of side branching, if you like. But I haven't been able to do the real problem. But you sort of get something not dissimilar on this, but only
But
on
I mean,
one
this
side.
finger eventually disintegrate with bigger and bigger wiggles.
It gets bigger and bigger wiggles as this gets further and further back, and I suppose I'm doing the limit as epsilon tends to 0, so I suppose when t is 1 over epsilon, the wiggles have got to be ordered 1, and then another regime takes over.
I believe Mike Berry wrote a paper saying that the error function is universal for Stokes smoothing, but then did you write a later paper saying it's not? Have I got the right end of the stick?
Yes,
there?
you have.
Well, would you like to expand on this? It's a really interesting observation.
It's universal for factorial over power of that form, but if you have a series which, let's go back a few years now, if you can have series which diverge more quickly than that. If they're superfactorial,
Oh, I see.
then you get different. So you can effectively get a class of smoothings where the smoothing function is e to the minus some polynomial in z squared. And so you have that sort of smoothing function. So if this was just z squared, it's error function, but you could do z4, z6, and in fact you can do any.
And these are clearly quite reasonable problems. You don't have to be artificial to get away from
I never found a differential equation that gave it to me. So I had to cook up a problem that did give it, so Mike's quite happy to write down an expansion and not worry about where it came from, but I wanted to know where it came from. So I did cook up a problem that gave me superfactorial divergence. So it's overwhelmingly the most common, but not quite universal.
So sometimes I find it hard to motivate the factorial over power ansatz for large n away from any singularities. You make the argument that you've got a singularity in repeated differentiation, looks like that. But how do you motivate that away from all of that?
So you can think of doing a Laurent expansion if you want, where you just said you've got poles at each of the singularities, and you do a full Laurent expansion. I mean, it is basically Darboux theorem, right? That you repeatedly differentiate and you see the singularities. I guess the fact that you don't just see 1 over z, but you've got to see 1 over some function of z. I don't know, how do you motivate WKB?
Well, I guess what you just said, I would say that it's not, it's power of this chi function, and the chi function makes it all fit.
Yeah, so I mean, often when you do the smoothing, if chi is not simply a multiple of z, then you switch to chi as the independent variable. And then you can sort of see why it comes.
If there's no more questions, let's thank John again.